Welcome in. In this video, we're going to discuss rapid spanning tree. Now, I know that we've discussed a little bit about rapid spanning tree as we've gone through the other slide decks and through the lab that we've just completed. However, I wanted to stop at this point and talk about rapid spanning tree in depth, at least as in depth as the CCNA gets. And of course, after this slide deck, like we did with regular spanning tree, we'll go back to our lab and show you how rapid spanning tree works and do the little convergence test like we did with regular spanning tree. So without further ado, what is ado and why would we want further of it? Let's start our discussion. Now, as we've seen in our lab, 802.1D spanning tree can take a long time to converge in the event of a network failure or a network recovery. You'll see that we failed our network. We saw it took about 20 seconds for the network to figure out that something had failed. Then we fixed the failure, and it took another 20 seconds for the network to realize, oh, you fixed this failure, I need to reconverge again. And as we've discussed, Cisco's proprietary extensions to spanning tree, the portfast and the BPDU guard extensions, they help this convergence issue, but obviously since they are Cisco proprietary, they don't work with non-Cisco equipment. So if you have a Juniper or an HP switch, you can't use portfast on an HP switch. It just doesn't support it. At least it's not called portfast. The IEEE came up with a new spanning tree protocol to address these issues, and it is the 802.1W RSTP, Rapid Spanning Tree Protocol. Now, as we'll discuss, RSTP is very similar to the 802.1D, the old spanning tree protocol. And in fact, if you happen to have some switches on your network that don't support RSTP, for those network segments, switches that are configured for RSTP will actually fall back and support the standard 802.1D spanning tree protocol. So first, let's start off and talk about the similarities to the spanning tree protocol. Like spanning tree, RSTP elects the root bridge using the same criteria, which is the priority plus the MAC address. It chooses a root or designated port on each switch using the same criteria. For root ports, it is the shortest path to the root, and for designated ports, it is the highest priority port on that particular network segment. And of course, rapid spanning tree forwards traffic or blocks traffic based on the same criteria, although blocking ports act a little differently in rapid spanning tree than they do in regular spanning tree, and we'll talk about that here in just a bit. Obviously, there are some differences between regular spanning tree, or what's the point of having the RSTP protocol? Rapid spanning tree has different port types and port roles than the regular spanning tree protocol, and I've got a couple of tables that show this a little later in the slide deck. You know how I mentioned that blocking ports act a little different? Well, in the rapid spanning tree, they're called discarding ports. In regular spanning tree, if you have a port that is blocking, it's not processing anything across that port. It's ignoring BPDUs, it's ignoring network traffic, ARP requests, MAC table entries, so on and so forth. It just acts like you've unplugged the cable from that port. With rapid spanning tree, you still aren't going to forward ARP requests and MAC table updates and user traffic through a blocking port, or a discarding port, as rapid spanning tree calls it. However, it will still listen to the BPDUs coming in on that port so that it can determine, yes, I can still get to the root going through this other port. And we'll talk about how that all works here in just a little bit. It's really kind of neat how it all works. In rapid spanning tree, the listening and learning states don't take 15 seconds each like they do in the regular spanning tree. All of this adds up to faster convergence, and you'll see this in the lab. We'll go through the same process of breaking our spanning tree VLANs while we're running that continuous ping, and you'll see that instead of taking 20 seconds, it takes about 5. So now that we've talked about some of the similarities and differences, let's focus in on the differences because we already know how regular spanning tree works. Let's start off with the port states. Now, you'll recall in regular 802.1D spanning tree, you had the 5 port states. Well, 4 technically. Disabled is the cable's unplugged or it's admin down or something like that. But you've got blocking, listening, learning, and forwarding. With rapid spanning tree, you only have 3 potential port states. If a port is not forwarding traffic, it is said to be discarding, and that corresponds with either the blocking or the listening state in 802.1D spanning tree. Again, if you'll recall just from the last slide, when a rapid spanning tree port is in discarding state, it will still listen for BPDUs in case its root port goes down, but it just won't act on those BPDUs unless it's needed. Learning and forwarding are the same port states as in regular spanning tree, although as we've mentioned, the learning state doesn't take 15 seconds like it does in regular spanning tree. Let's move on to the next slide. Now we'll talk about the port roles, and you'll recall in our lab I mentioned the port roles because it's listed in the newer iOS switches, even though the port roles really aren't used in 802.1d spanning tree. Now the root port and designated port in rapid spanning tree are exactly as they are in regular spanning tree protocol. The root port is the port that has the best path to the root, the lowest hop or the lowest port cost. The designated port is the same as spanning tree. It's the best port on a given network segment. And as you'll recall, rapid spanning tree uses the exact same criteria to determine the root and designated port. However, rapid spanning tree also introduces two other port roles. We have an alternate port and a backup port. Alternate port is the magic, if you will, of how rapid spanning tree converges so much more quickly. An alternate port is generally a discarding port. It's a switch port that's receiving a suboptimal path to root. Now this particular port type doesn't necessarily forward traffic for that segment. It does not necessarily have to be a designated port. It could be a discarding port. However, rapid spanning tree realizes I can still get to the root going through this alternate port. So if I lose my root port, after 3 times the hello timer or 6 seconds, I'm going to say, well, my path to root is gone. Do I have any alternate ports available to me that I can start forwarding traffic out immediately? Oh look, there's an alternate port here that can still get to the root. I'll just switch and make him the root port, and it doesn't have to go through the whole discovery process like 802.1d spanning tree does. Now obviously if the switch doesn't have any alternate ports, it will still have to go discover a new root port, but most switches, if you have redundant links, will have an alternate port available to it. And the last new port type in spanning tree is the backup port, and I've got a little network diagram on the next slide that kind of makes this a little clearer. But a backup port is a switch port that's connected to a shared media segment, i.e. a hub. So if you have a switch and it has 2 ports connected into a hub, one of them is going to be a backup port. Obviously it can't forward traffic out that backup port because it will create a loop in the network. So it's kind of like an alternate port, but it's an alternate port that's not connected to another switch. And as I promised, here's my lovely little network diagram. Looks suspiciously like the one in the regular spanning tree slide deck. Well, it pretty much is. Up here we have the root bridge, and you can tell because all of its ports are designated ports, so it is the root bridge. We have a hub over here as well, and we have our 2 non-root switches down here at the bottom. So obviously each of these switches have a root port pointing back to the root, like so. This switch over here on the left, however, is not the designated port switch for this network segment at the bottom. Even though it appears like it's just 2 switches connected together, you can imagine 125 workstations on this particular segment. However, because we are running rapid spanning tree, this switch over here has an alternate port. So this switch says, this port over here is not my root port. However, I can get to the root going through this switch port, just not as efficiently. So it will not forward any traffic on this port, but it will still listen to the BPDUs from this switch over here. If this link were to ever go away, this switch would know, well, I have an alternate, I'll just send the traffic out this direction. Now let's examine this link up here to this hub. Now obviously when this switch sends out BPDUs on this link, it goes over to the hub, just broadcasts everything that it receives out every port on the device. So it will send that BPDU out this other link back to the same switch. This switch will realize I sent a BPDU on this port and I got the same BPDU back on this second port. Therefore, these 2 ports must connect to the same hub, so I'm going to flag this one as a backup. Now, it will not forward traffic out this port, as I mentioned. However, should this designated port go down, someone goes and unplugs this port from the hub on this end, this switch will realize I still have this backup port, and so I'll switch over and start using it immediately, much like this switch down here did with its alternate port. So let's examine rapid spanning tree in normal operation. Let's say we have a network with 4 switches and they're all connected like so. You'll see this on a lot of networks. It's just daisy chained like this. And let's say we as a network administrator see this setup and we go, well, that doesn't offer any kind of redundancy whatsoever. If this link here were to go down, this entire half of the network would just be disconnected. You'd split the network in half and you couldn't get to the servers that were up here on this top switch. So we're going to implement some redundancy and we put in another link between these 2 switches. Now because we are running rapid spanning tree, this switch down here at the bottom right immediately says, hey, I'm starting to get BPDUs from the root bridge on this other port over here. I'll tell you what, I'm going to block all of my other ports to other switches, and if we have 5 or 6 other switches here, you can imagine the same thing on those links. I'm going to block all of my other uplink ports, and I'm going to tell this switch, you start sending all of your traffic for my MAC addresses out this port. And so almost immediately, you start using this new uplink port between the root bridge and the non-root bridge down here at the bottom right. Once this switch has determined that there's no loop on the network, it says, fine, I'll start sending BPDUs out all of my ports again. So it brings this link back up and starts sending BPDUs to this switch. Now this switch is receiving more optimal BPDUs for the root bridge coming from this direction as it would from this direction. So this switch here does exactly the same thing. It says I'm going to block all of my other uplink ports until I can determine that this path to root is more optimal than the one that I had before. And again, once this switch determines that there's no loops on the network, it then brings this port back up. But now it's getting BPDUs from both directions. So it says, well, you know what? This path here is just as efficient as this path here. So I'm not going to change anything unless one of these links down here happens to fail. Then I also have an alternate path back up to the root going this direction, and I can use it immediately without having that 20 seconds worth of convergence that regular spanning tree does. And that concludes our discussion of rapid spanning tree. Stay tuned, we'll put all this in a lab and it'll get a lot more interesting, I promise.